So we left off last time talking about phase changes and how heat causes an increase in temperature. But remember, heat doesn't only have to cause an increase in temperature. In fact, sometimes you can have heat going into a substance and it doesn't change its temperature at all. And in that case, the heat is used not to change the temperature, but to change the what? The phase, right. So I left off with this graph that I sort of hastily sketched out. So let me go over this one more time. Here I have a plot, and on the y-axis is temperature, and on the x-axis is energy. Morning, that's okay. Come on in. Make sure I started this. On the x-axis is energy. So as I go along here, I'm adding energy. So this could be like putting a pot of ice on the stove, and as time goes along, you put more and more energy into the pot of ice. So if you want to think of this as time and not as of energy, that's okay. As I move from left to right, the time increases as I have my pot on the stove, a pot full of ice. All right. Here, my ice is really cold, below the freezing point of water, and as I add more and more energy, it raises it up to the freezing point of water, but it doesn't convert any of it to water until I get to this point. And then, at 0 degrees Celsius, it begins converting that ice into water, converting it into water, but not changing the temperature. This actually requires quite a lot of energy in order to convert from one phase to another. So a lot of energy in order to break those bonds within the ice and cause it to convert into water. And then when all the ice is turned into water, only then does the actual temperature of the water begin to increase. Now all along I have this pot sitting on the stove. When it actually gets up to the boiling point of water at 100 degrees Celsius or 212 Fahrenheit, it will actually begin now converting into steam. And of course, that also requires more energy. In fact, it requires more energy to convert into steam than it does to convert from ice to liquid water. So for a time there, as energy is pouring into the substance, I get a combination of liquid and gas as it makes some of the water into steam. Some of it remains water until I get to this point when it's all steam, and then you can raise the temperature of the steam. And the steam can go on and get as hot as you want it. Until the point that you actually ionize the gas, and that is a fourth state of matter. We did not talk about that, but do y'all know what the fourth state of matter is? Right, it's a plasma, and that means that you strip the electrons off of the nucleus, and it becomes an ionized gas. You don't see that; those are very hot temperatures. So you see them on the surfaces of stars, for example. It's very commonplace. You can create them in the lab, or if you ever go to that really shady store, Spencer's. You ever been to that store? Okay, you can raise your hand. I went there once. Where they have the dog poop in a box. They have the ball with the arcs and stuff. That's a plasma. That's actually a low temperature plasma. The gas is being ionized in a different way through the electric voltage. All right. You don't need to know about plasmas, but they're kind of interesting. Now, we can calculate the amount of heat required for each of these points on this plot. So, for example, here, if I'm raising the temperature of the ice in this region right here, and I put in a certain amount of energy, I can calculate that energy. You may have seen this before. It's mc delta T, where here m is the mass. C is something we call the specific heat. I'll explain what that is in just a moment. And delta T is the change in temperature. Right? So M is the mass, C is the specific heat, and then delta T is the change in temperature. And I think I've defined Q already, but let me just say it again here. Q is just the amount of energy. And in this particular case, this is going to be thermal energy. All right? So I have a certain amount of mass, a certain specific heat, and a certain change in temperature. Now the specific heat is specific to the material. It describes the amount of energy required to raise the temperature of a substance? So for example, which has a higher specific heat? We're called a higher specific heat. Is it A, wood, or B, metal? Which has a higher specific heat? Let's try this as a clicker question. Which has a higher specific heat? Is it A, wood, or B, metal? Which one requires more energy to raise the temperature of that substance by a certain amount? Which has a higher specific heat? I think you probably know this intuitively, so if your intuition is telling you an answer, then please answer that way. Most of you are right now. All right, most of you have the right answer, but let me try to coach you a little bit on it because we haven't told you this explicitly. But imagine if I take a piece of wood or I take a piece of metal and I put it in the fire, right? Morning, Alex. The amount of time that it's in the fire is going to be correlated with the amount of energy that goes into the substance, right? So which one will get hotter faster? And the one that gets hotter faster will require less energy to increase in temperature. Right? It's also related, I understand, to thermal conductivity. How fast does it conduct thermal energy? But it's also related to the specific heat. Those two are closely paired. All right? Which one has the higher specific heat? So which would that be when you put it in the fire? The one that heats up more quickly or the one that heats up less quickly? Right, the one that heats up less quickly. Because it requires more energy to heat up. Is that heats up less quickly. Because it requires more energy in order to raise its temperature. All right, just a few more seconds. I'll stop at 2:05. Morning, ladies. All right, A is the right answer. Again, not something that you might know explicitly right off because you don't walk around knowing the specific heats of things, but I think that you do know the specific heat actually quite well. What has a higher specific heat, sand or water? Let's try this as a clicker question as well. Which has a higher specific heat, sand or water? Which has a higher specific heat, sand or water? Which heats up less quickly? That's the one that has a higher specific heat. Oh yeah, I'm sorry. Which is it, sand or water? Which has a higher specific heat, sand or water? Right, about 10 or 15 more seconds. We'll stop at 33. Okay, imagine you go to the beach and you're there, say at noontime, and the sun has been beating down on the sand and it's been beating down on the water in the same way. Which one's going to heat up more quickly? The sand, right? That's why the beach gets really hot, because sand has a really low specific heat, but water has a really high specific heat. So it doesn't heat up nearly as quickly because it requires a lot more energy in order to raise its temperature. So water then has a higher specific heat than sand. We'll see that again in a little bit when we do some more clicker questions. All right, let's just do a quick calculation. let's say that I have a kilogram of water. I have a mass of 1 kilogram of liquid water, and I want to raise its temperature. My initial temperature is, I don't know, let's say 30 degrees Celsius, and my final temperature I want to be, say, 40 degrees Celsius. So it's going from, I don't know, about 80 degrees Fahrenheit to 100 degrees Fahrenheit. 30 degrees Celsius to 40 degrees Celsius. And I want to know how much energy is required in order to do this. If I know what the specific heat of water is in calories, it's what? No, it's 1, right? I'm pretty sure. The specific heat of water is 1. That's 1. This is actually how we define a calorie. It's 1 calorie per gram per degree Celsius. So we define a calorie based on how much energy is required to raise 1 gram of water by 1 degree Celsius. We'll see that in just a bit. But that's the specific heat. It's a constant. You can determine it experimentally. And then I want to know what is the amount of heat required. And so I can calculate this. It's going to be a kilogram, which is, I'll need to convert that into grams. That's going to be 1,000 grams. Remember, kilo means 1,000. The way that I know that I need to convert it into grams is because I see here in the specific heat that I have grams in my denominator. I have 1,000 grams times the specific heat, which is 1 calorie per gram degree Celsius, times the change in temperature, which is going to be 10 degrees Celsius. Right, that's just going to be 40 minus 30, which is 10 degrees Celsius. So that's 1,000 times 10. So that's going to be 10,000 calories. Right? That's a basic calorimetry problem. How much heat is required to raise the temperature of something by a certain amount? All right? We'll see some more of that in just a bit. Now, there's also this idea that if I take a hot substance and place it into a cool substance, that it will come to an equilibrium temperature. Remember what that was called? What is it? No, it was called thermal equilibrium, right? And thermal equilibrium occurs when what is true about the substances? They are at the same temperature. So substances are in thermal equilibrium when they are the same temperature. Now, calorimetry is a very useful way to determine how much heat flow you have between two substances. So let's say that I have cool water. Right? And then I take some substance and I place it into the cool water. Let's say I take a hot substance. I place it in the cool water. I don't know, let's say that the temperature here of the water is 20 degrees Celsius. And let's say that this hot body has a temperature equal to 40 degrees Celsius. We'll actually see this problem in a little bit. I'm just going to set it up right now, but we'll see it in a little bit because we'll see this in terms of if you take a person that's feverish and put them into a cool bath, how much energy is lost. So I can say that the hot body has a certain amount of energy that's lost or gained. Does the hot person lose or gain energy when you put them into this cool bath? They lose energy. And so a basic principle of calorimetry says that if you lose energy, that something else has to gain it. And that those two are going to be equal. That any lost energy is going to equal the gained energy. Now here, what is the substance that's gaining energy? The water is gaining energy. So I could say then that my Q lost is going to be MC delta T. That's going to be the mass. We'll just go ahead and say that this is a person, because we'll see this problem a little bit later. And I'll actually put in numbers. I'm just going to set it up here. The mass of this person, the specific heat of the person, and then the change in temperature for the person. And then the gained energy is all going by the water. So the mass of the water, the specific heat of water, and the change in temperature of the water. So they're going to come to some intermediate temperature that will be in between 20 and 40. So at some point, they will both reach a temperature that is the same. So we'll say that they both have a T final. And so we can rewrite this equation that the mass of the person, the specific heat of the person, times my T final minus T initial. And T initial is going to be 40 degrees. So that's going to equal the mass of the water, the specific heat of the water, T final, minus what is my initial temperature here for the water? It's 20 degrees Celsius. It's fairly cool. That's about, how many degrees Fahrenheit is 20 degrees Celsius? About, roughly. You recall? It's about 70 degrees, right? So 20 degrees Celsius is about room temperature. That's about 70 degrees. You need to have a good grasp on sort of these basic temperatures. I gave them last time, but you could very well see a problem next time on the test. What is room temperature in degrees centigrade, or degrees Celsius is 20 degrees. Also, what is the body temperature in Celsius? Do you recall? 37. So those are two good temperatures that you just need to know. 20 degrees Celsius is the room temperature. That's about 70 degrees. And then 37 degrees Celsius is our body temperature. That's 98.6 degrees. So just need to know those for the exam next week. So here we have an equation. We could solve it. I'm not going to do that right here. And you're not expected to be able to solve something like this. But you could find what is the final intermediate temperature when these two objects come into thermal equilibrium. All right? We'll see a problem like this later when we talk about how we have cooling mechanisms for the body and what you do with somebody that's very feverish. Okay, now, if we go back to this plot, that deals with these areas. It tells us how much energy raises the temperature of a substance. But now we also want to know how much energy is required to change phases. And it turns out that it's quite a lot of energy to change from one phase to another. And the way that we do that is that we deal with something called the latent heat. I think that your book might just call it latent heat. Let me see. Yeah. Latent heat. I don't think that your book makes distinctions between the two latent heats, but there are actually two different latent heats. There's the latent heat of vaporization and the, gosh, the other one just slips my mind. Does anybody know? Fusion, thank you. The latent heat of fusion. The latent heat of vaporization is when it goes from a liquid to a gas, right? It becomes a vapor. And then the latent heat of fusion is when it goes from a solid to a liquid. Because you think of fusing things together, like you fuse water together to become ice. So those are where those come from. You may have heard those before in high school chemistry or college chemistry. All right. Now, the latent heat is the amount of energy to change phases. Either going from solid to liquid or liquid to gas, or vice versa. So for example, if you're going from a solid to a liquid, you have to put that energy in. You have to put in latent heat. But if you're going from a liquid to a solid, you have to take away that energy. So it's quite a lot of energy to take away from water to make it become ice. Right. You don't need to know that, but I'll write it here. The latent heat of fusion is liquid to solid, or vice versa. But you don't need to know this, so don't write this down. I'm just for your own reference. And the latent heat of vaporization is from a liquid to a gas. And those have different values. So the latent heat of vaporization and the latent heat of fusion for water is quite different. It actually requires a lot of energy to make water go from being a liquid to a gas, which is why sweating is such a good cooling mechanism for the body. Because in sweating, you're having which of these? Fusion or vaporization? Vaporization. And so when you have water on your skin, as you all know, I'm sure that you know this, when you have water on your skin, it evaporates, it becomes a vapor. It carries away a lot of energy from the body, a lot of energy. So sweating is a very effective means of cooling the body. Okay, so these latent heats, these are constants. You can look them up in tables, and our amount of energy required to change from one phase to another. Oh gosh, let me see. People use different things for this. Let me see what your book uses. I think they use an L, if I'm not mistaken. Yeah, they use an L. So it is equal to the mass times the latent heat. And over here, if you want to know this, the latent heat of fusion, the latent heat of vaporization, LF or LV. As I said, those are different for different things. All right? So in this way, if you just know the mass of the substance, you can figure out how much energy is required in order to make it change phase. I want to share with you a little clip. This is actually like an interview that they're doing at a lab. It's a food science lab where they're trying to determine the caloric content of food items. And what they do here is that they take, in this clip they use fruitcake because this is like a holiday clip, it's a radio clip. They're taking a piece of fruitcake, just a tiny little piece of fruitcake, and they put it into what they call a bomb calorimeter. You ever seen a bomb calorimeter? Some of you have or heard of one? No, what they do is they put it in there and they basically explode it. So they put a certain amount of energy required to vaporize it, and then they measure the rise in temperature. And that rise in temperature will come from the energy that they put into the calorimeter, but then there's an additional amount of energy that comes from burning up the fruitcake. And they use that to determine the total amount of food energy that's in the fruitcake. And then they do this over and over again, and they average all together. And then that's what goes on the nutrition information thing on your food labels. So let's listen to this. It's just a radio clip, but I think it's fairly interesting, where they use calorimetry to determine the energy content of food. Let's look now at thermal conductivity, and we'll see this a little bit later when we're talking about the cooling mechanisms of the body again. Thermal conduction. All right, thermal conduction is the rate at which energy leaves a substance. And anytime we have a rate, that's going to be something per unit time. So our thermal conduction in its basic form is just going to be Q over T, where Q is the thermal energy and then T is the time. Anytime you see a rate, that's going to be something per unit time, like a rate of speed, that was our distance over time. And so here our thermal conduction is just our energy per unit time. And this is proportional to a few different things. It's proportional to K, which is conductivity. I'll write that in just a second. A, which is the area of the body, delta T, which is the difference in temperature, divided by the distance from the substance. So K here is the thermal conductivity. All right, thermal conductivity. This is a constant. It changes for different substances. So for example, we've talked about this before, but wood, for example, has a much higher K, or excuse me, a much lower K value than say metal does, because it doesn't conduct very well. So if K is small, that means that this rate at which energy is transferred is small. So wood has a very low K value, has a very low thermal conductivity. It's a constant value determined experimentally. A is the area of the substance, or area of the object. We'll look a little bit later and we'll consider the area of a human body and how quickly it transmits energy to its surroundings. T is the temperature difference. So if I go outside on a 100-degree day, the difference between me and the temperature of the surroundings of my body would be, 1.4 degrees Fahrenheit. Whereas, and so my heat exchange would be a certain value. But if I went to the South Pole or wherever, I would have a much larger difference between my body temperature and the temperature of the surroundings. And so then, obviously, I'd have a greater transfer of energy. And then D is I said distance. It's actually the width of the material. We'll see this in an example later, and in the example later, we'll consider the distance between your core of your body to the outer part of your skin, which isn't very far. It's just about a centimeter or so, and we'll consider that. How quickly does energy transfer between the outer shell of your body or the skin of your body? Right? So that's our thermal conduction, and it's related to those things. You should be prepared to answer questions regarding, well, if the temperature difference is larger, how does that affect Q? Or if the width of the material is larger, how does that affect Q? Let's just ask a couple questions here. So if A is big, that is, you have a large surface area of whatever object, Q over T, is it big, or is it small, or does it remain the same? So if you increase the surface area of your object, does the rate of thermal conduction, does it increase, does it decrease, or does it remain the same? If you increase the surface area of your object, does the rate of thermal conduction increase, decrease, or remain the same? All right, I'll stop at 45. Okay, very good. A is the correct answer. If I increase the surface area, then it's going to give off more energy, or it's going to take in more energy at a faster rate. And you can see that here, that if A increases, Q over T also has to increase, given all the other things are the same. Now let's imagine, instead of A increasing, let's say that D increases. So let's say that, I don't know, your skin is this wide, but then you make it a lot wider, right? How does that affect? It's like you put on a coat, basically. How does that affect the rate of energy transfer? If D increases, does Q over T, does it A increase, B decrease, or C remain the same? If D, the width of your material, the distance over which the energy is traveling, does Q over T increase, decrease, or stay the same? Stop at 35. Okay, well, B is the right answer here. You can think about it intuitively, right? It's like me putting on a heavier skin, right? If I put on a heavier skin or a thicker skin, then my body isn't going to lose energy as quickly, right? Yes? That if D is bigger, that energy is just not going to travel through there as quickly. Or you can think about it mathematically, which is probably the better way, is that if I increase D, that is, if this value goes up, then this value has to go down. Let me show you that with some numbers. What I'm saying here is that if D goes up, then Q over T has to go down. Think about a fraction, right? I have 4 is equal to 6 over 3. All right. Well, what if I increase this value? What happens to 4? It would actually decrease. Like if I said instead 6 over 3, I made it 6 over 6, then that would equal 1. So if I increase the denominator, the other side, the opposite side of the equation, everything else held constant is going to decrease. That's right, Kayla. Yeah, so if I increase the change in temperature, Q over T increases. And you can think about that, right? If I go outside on a 100-degree day, I have a certain heat exchange with my surroundings. But if I go to the South Pole where it's like minus 100 degrees or whatever, I'm going to have a much greater rate of heat exchange, which is why I want to increase D as much as possible by putting on big, thick coats and what have you. All right, to decrease that heat exchange as much as possible. All right. We'll see that again in just a bit, either today or next week. All right, let's look now. Oh, so this is in regards to conduction, thermal conduction. And this is going to be one of 3 rates or 3 methods of heat exchange that we'll look at. Thermal conduction. Conduction just occurs when you have something touching something else. All right. So it requires contact. And in regards to the human body, it can be that you're actually touching something that's cooler than you are or something that's hotter than you are. Or it can be that you have a gas around you, that you have air around you that's cooler, and then you heat up that air, and that's the rate of heat exchange. That's what that's the flow of heat from you to the air. So it doesn't have to be a solid substance. It can also be that you're in contact with a gas or a vapor or a liquid. The second of these is called convection. And this is similar to conduction in a sense, but it requires the flow of a fluid around an object. You know what a convection oven is? How is a convection oven different from a regular oven? I know many of you might not have convection ovens, we don't. But how is a convection oven different? Right, they have a fan inside, and they circulate the air. And that causes you a much greater transfer of heat from the oven to the food substance, because you're continually replacing the air around the cake or whatever it is you're cooking. All right. So if I have air around my arm, there's contact between the air and my arm, and that's what type of transfer? That's conduction, right. But when that air warms up, it goes away, and it's replaced by cooler air. So there's this combination of conduction and convection, because I have this continual flow of a fluid around me. And a fluid, remember, includes anything that flows. So it could be not just a gas, but also a liquid. Like, for example, in a whirlpool bath, right? You're continually replacing the fluid that's around the person or around the object with a fluid that's a different temperature, be it cooler or warmer, whatever you want to do to the person. Right, so convection, just know what it is. It involves the flow of fluids around an object. The third is radiation. There are equations, by the way, to describe the rates of energy transfer for both convection and radiation. But as you can imagine, they're quite a bit more complicated than the rate of conduction, so we're not going to do them here. Radiation involves the transfer of radiation. Or you can say maybe light, which is a type of radiation. I'll just do e.g. light, from one substance to another. You hold your hand up next to a light bulb, not so much these light bulbs because they're fairly cool, but up next to an incandescent light bulb, and it's fairly warm, right? Do you have to touch the light bulb in order to feel the warmth of the light bulb? No. In fact, if I brought in a bunch of light bulbs in here, it would heat up this room. We'll find also that we give off radiation. We give off light of a sense. Do you know what type of radiation we give off? Anybody know? Okay, we use this. This is the type of radiation that's used to warm things, or that comes from warm things, and we're warm things. What kind of radiation is warm? When you think of warm radiation, huh? Okay, thermal radiation is a name for it, but it has a more particular name. It's called infrared radiation. We'll see this a little bit later. You're all like a bunch of little infrared light bulbs. And in fact, you're about 100 watts of power, which we'll see in a little bit. So each of you are like a 100-watt infrared light bulb. And in fact, your body loses most of its energy because you're walking around glowing like an infrared light bulb like all the time. You never turn off. That's kind of neat, I think. Don't you think? You're like all little light bulbs sitting. And that's why when you're in a room, the room heats up. It's not because of conduction. Right? You're not touching anything that's causing the room to warm up, though your chair might warm up. That is conduction. And it's not really convection either, although that could play a part. But it's mainly radiation. When you have a lot of people in a room, it's because of the radiation of each individual body. So I think next time you go to a large gathering, right, it gets hot, then you can say to your friend, you can say, boy, there sure is a lot of what in here? Radiation. There sure is a lot of radiation in here. All right? And then they'll think that you're cool, and they'll think that you're, I don't know, they'll want to be your friend. What? Okay. All right, so 3 types of heat transfer: conduction, and you'll need to know how those things are related to the area, the temperature difference, the conductivity, and the width, d, of the material. And then also convection requires the flow of a fluid, like, for example, in a convection oven. And then also radiation, like, for example, a 100-watt light bulb, of which you are one. Okay. All right, can I move on from here? All right, now we're moving into the section on the body, energy in the body. I think this is on page 92 of your book if you're following along. Energy in the body. And we'll revisit some of these ideas. But a governing principle that we'll use here is the conservation of energy. We've already seen this. This is a principle that's true always for any closed system, and that is just that there is no lost or gained energy in a closed system. No lost or gained energy in a closed system. It's sort of a circular definition, right? Like we say a closed system, and a closed system is defined as there's no energy coming in and there's no energy going out. And then we're saying, well, there's no lost or gained energy in this system where there's no energy coming in and no energy going out. But nonetheless, it's still a law, and it's always true, that this is going to hold true, that if we have a system, no energy going in or out, then it'll be a closed system. Also, the idea of the work energy theorem. And the work energy theorem just said that work is basically equal to a change in energy. So anytime you do work, you're going to consume energy, is basically what that's saying. And that should be fairly obvious. But just to put it into a formula like that, because we like to do that. Anytime you do work, raise a dumbbell, walk upstairs, whatever, you consume energy. And, well, you do, maybe it's better to say your body consumes energy, okay? Yeah, so anytime you do work, your body consumes energy. And of course, that energy comes from the food that we eat. So anytime you do work, you consume energy. And that's, as I said, it's just a work energy theorem. We introduced that early on in this chapter, likewise with the conservation of energy. But those two will be sort of guiding principles. They've been guiding principles all along, right? Like with calorimetry, saying Q lost equals Q gained. That's really just a restating of this conservation of energy. We're saying that any thermal energy that comes into one substance has to be lost by another substance. That's really just conservation of energy. All right. Food is our primary source of energy. I guess we could say it's our only source of energy. Is that true? Is there any other source of energy for the body? You get, I guess you get energy from the sun, for example, right? Because it can heat up your body. You can get energy from surroundings as well, how they change the temperature of your body. But food is our primary source of energy. They introduced two terms in the book. You probably know this, but this energy can be stored in the body, which is a pretty handy thing. Energy can be stored. It can be stored for short term. And this type of storage called, you know, glycogen. Glycogen stores. I don't know exactly what glycogen is. Does anybody know? School me, huh? Glucose and what? It's a chemistry thing. It's sugar. Thank you. So for a short term, oh, that's misspelled. I'm sorry. Glycogen. And then you can also store it for long term, for those long times when you're going to be short on food. And of course, that will be fat storage. So you can have short term, that is that energy that you can use really quickly if you're running from a tiger or whatever. And then you can also have long term storage for those famines that you might face, and you can store fat. All right. So energy from food, we're going to measure in calories. Go down from here. The unit of energy is a calorie. And as I said before, the calorie is defined, as well as the specific heat of water. It is defined as the amount of energy required to raise the temperature of water. The temperature, excuse me, of one milliliter of water by 1 degree Celsius. All right, to raise it from, say, 40 degrees to 41 degrees, or from 38 degrees to 39 degrees, or 10 degrees to 11 degrees Celsius. All right, I say 1 milliliter, but 1 milliliter of water is equivalent to what? It's equivalent to 1 gram. In fact, you know, the gram used to be defined as, we know that it's not anymore, but the gram used to be defined as based on the mass of water. You recall a gram was a cubic centimeter of water, or the kilogram was a cubic liter of water. All right, so our liter of water. So 1 milliliter, which by the way is the equivalent of 1 cubic centimeter, is also the equivalent, way to draw this, is the equivalent of 1 gram of water. All right, so 1 milliliter of water has a mass of 1 gram. This is a good definition to know. It's a good number. It's a nice round number, good easy number. But that's how we define what a calorie is. Now, when we talk about food calories, they're not actually the same. A food calorie which we abbreviate with a capital C, or CAL, is actually how many of these calories? 1,000. Yeah, so one food calorie is actually 1 kilocalorie, as you might see. And in fact, if you get things from Europe where they use the SI system, they'll use either kilocalories or joules to list the food content and not the big C calorie like we use. Or this is also 1,000 calories. Right? So when we talk about calories, we're really talking about 1,000th of a food calorie. Right? There are three food sources of energy. So 3 types of sources among food for energy. Can I go down from here, folks? 3 sources of energy from food. And these are carbohydrates, pastas, sugars, I don't know what else, carbohydrate, rice, yeah, grains. The second are lipids. That's just a fancy way of saying what? Fats, right? So that's the way who would say fat? Fancy Nancy. Yeah, so that's fats. I have this song in my head. Y'all know Olivia? Olivia, Olivia. I've been singing that song all morning. And proteins. Proteins you get, of course, from meat, beans, stuff like that, soy products. These have a particular amount of energy per gram. Carbs and proteins both have about 4 kilocalories per gram. That is, carbs and proteins both have 4 kilocalories per gram. And do lipids have more or less than that, you think? They have quite a bit more. So they have about more than twice that amount, or 9 kilocalories per gram. Now, beer is a big source of carbohydrates. Is that what you're saying, alcohol? 7? Seriously? All right. Okay, so anyway, those are 3 sources of food from energy, and they have different sources of energy. And these numbers, they're sort of just average numbers. But lipids typically do have more energy per gram than do others. These collectively are called nutrients. They're not the only nutrients that the body needs. What are some others? Vitamins and minerals, and then one really big one, water. So other nutrients include vitamins and minerals, which you only need a small amount of, but they're very important. And then the other big one is water, which plays a big role in a lot of different things in your body. Your book said this, and I know this sort of changes, and I wouldn't quiz you on this because I think this might change with time. Your book recommended a diet of 50 to 60% carbs. I don't know when this was written. 50 to 60% carbs, 20 to 30% fats, and 15 to 20 from proteins. I think that like new recommendations don't follow these guidelines, right? Is that true or no? It depends on your diet and sort of what you do. Okay, we'll talk about that in a bit. But like for example, like an endurance athlete would want to have more of what? More protein? Really? I thought like endurance athletes eat a lot of carbs. They just eat a lot, right? Okay. All right. Well, I'm not going to ask you about these percentages, but this is what they say in your book, and I'm not sure if they still hold true. Y'all probably know more about that than me. All right. All right. Let's look at work done by the body. We'll do some simple calculations. Hold on, let me look at something. Okay, yeah. Turns out that work done by the body is not really a big part of your daily consumption of calories. Like when you exercise, you use a certain amount of energy, but it's actually not a big portion. It's a very small percentage of your overall consumption of calories by your body. Let's do some simple calculations. For example, let's say that we want to climb one flight of stairs. What is the minimum amount of energy required to do that? So I have some stairs. I'm going to go from here up to the top of those stairs. And I want to know just what is the bare minimum amount of energy, right? Well, the bare minimum amount of energy, assuming that you lose no energy between this point and this point, is going to be found just by our change in our potential energy. Remember we talked about potential energy? Gravitational potential energy is equal to the mass times the acceleration due to gravity times the height. That's the bare minimum of energy required to take a mass from one point up to another. As we know with the body, that's not all that there is, because it turns out that the body is very inefficient, that muscles are very inefficient in doing work. But let's first just calculate what is the potential energy. Well, let's say that our mass, let's just use 100 kilograms. That's a pretty big person, but typical person is usually about 70 kilograms. But to make our numbers right, our numbers easy, let's just use 100. G, of course, is 10 meters per second squared. And let's see, flight of stairs roughly is what? How many meters? About 3 meters, right. So a flight of stairs is about 10 feet or about 3 meters. So H here is about 3 meters, which is about 10 feet or so. All right, so if I want to know my bare minimum potential energy, it would be just mgh. That's going to be 100 kilograms times 10 meters per second squared times h, which is 3 meters. So let's see, that's 100, 1,000, that's 3,000 joules. That's my potential energy required, or that's the energy required by my body, the bare minimum to move from one point to another. Let's see, that is roughly, it's not quite this, but I'm going to use this number because it's pretty close. That's roughly about a half a kilocalorie in order to do that. So that's not very much, right? It's like a half, I don't know what that was. I think maybe it's that little cube of fruitcake maybe. But a half a kilocalorie, so not very much. So then if I went 200 flights of stairs, how many calories would I burn? I'd just do 200, so if I climb 200 flights, you know, for one flight of stairs, we had a half a calorie, half a big C calorie. So for 200, I would just say 200 flights on a times 0.5 calories. These are big C calories, so those are kilocalories per flight of stairs. So I would only burn 100 calories. That's like one of those little packs of cookies, right, or the little crackers. But that's 200 flights of stairs. That's a lot of stairs. That's probably an hour or more on the stair stepper at a pretty vigorous rate. All right, so 100 calories. But we know that that's not the case, right? That actually, when we do something like that, we actually burn quite a bit more than 100 calories to climb 200 flights of stairs. Right, y'all aware of this? Okay, so we do burn quite a bit more than that. And the reason is that muscles are very inefficient. They're very inefficient. They typically have a 20% efficiency. Did we use E to describe efficiency? You'll recall? I'll just write percent efficiency. It's typically a 20% efficiency for your muscles. That means for all the energy that comes into them, only 1/5 of it becomes usable. All right? So, for example, let's say that you climb stairs and burn 500 calories. 500 big C calories. By what amount have you increased your potential energy? All right, if muscles are 20% efficient and you climb stairs and you consume 500 calories, by what amount have you increased your potential energy? Let's do it as a clicker question. Let's see, is it A, 500 calories? Big C calories, excuse me. Is it B, 100 calories? C, 200 calories? D, 250 calories? I'm sorry, these are all big C's. Or is it E, 1,000 calories? All right. So you climb stairs and you burn 500 calories. That's the total amount of energy that your body burns. But by what amount have you increased your potential energy if your efficiency is only 20%? All right, I'll stop at 105. 105. What was B? Hey, that's right. Very good. So a fifth, only a fifth, because you're 20% efficient, only 1/5 of your total energy actually goes into changing your gravitational potential energy. All right? And that's where our efficiency comes in, that our bodies are really terribly inefficient. So we actually use a lot more energy than we expend, than we actually produce usable energy. That energy goes into what primarily? That extra 400 calories, it goes into heat, right? Because you're walking around like a 100-watt light bulb, giving off all this heat, and so that extra 400 calories goes into heat. And some of us give off more heat than others, which gets us into metabolism. Right? Metabolism, biochemical reactions in the body. That use energy to build up and tear down substances. When I talk about building up things, that would be like, for example, doing what? If your metabolism acts to build up things, for example, doing what? Like repairing muscles that are damaged, or what? Repairing things, right? Repairing things in the body that are broken, basically, are producing new cells, new skin cells, and what have you. Are tearing down substances. Well, when would your metabolism tear down substances? Okay. Um, no, I was getting to food. Like when you consume food, maybe so. I'm not sure if that would fall under that definition. Anyway, consuming food, it does break down those substances to convert them into a useful energy. Right. So your metabolism does these things to build up and tear down substances. We'll talk about the metabolic rate, and next time we'll get quite a bit into this, the metabolic rate and how it's affected in different ways. It's just the rate of energy usage in the body. And to measure the metabolic rate, there are a couple different ways that you can do this. In your book, they describe a way which I thought was interesting. I'm just going to call this MR, the metabolic rate. To measure it, you can submerge a person in a tub of water. And measure the increase in temperature. The change in temperature of the water. So if you imagine that you have this tub of water, and then you put a person in it, which as we know is really just like a light bulb, then that light bulb or that person is going to cause the temperature of the water to increase, and you can figure out what is the power rating of this light bulb, or what is the metabolic rate. So is this a 100-watt bulb, or is it an 80-watt bulb, or is it a 120-watt bulb? And people are all going to be a little bit different on their metabolic rate. But they put a person into a tub of water, and then they measure the change in temperature. I have a little clip here, and we'll wrap up with this. This clip just describes how they measure the metabolic rate in other ways. They can measure your heart rate while you're exercising and your breath rate, and they can actually calculate what is your metabolic rate. So we'll watch this, and then let y'all go. But I'm going to hand back your quizzes. Oh, where is it? Oh, I think I put it on my YouTube channel. Let me check that out. Oh yeah, here we go. So it's just a little news clip on some local TV station about measuring metabolic rates.